Well, welcome to our discussion of sedimentary rocks. It's the second type of rock type, or second rock type we're going to kind of cover in this class. And again, we're going to focus on roughly how they form and then the environments that we might find them in. Sedimentary rocks are different than igneous rocks or metamorphic rocks, and then they really form at or near the Earth's surface, or within the first 10 kilometers of the Earth's surface. Primarily, they exist together. Sediments, by definition, are loose minerals. Feldspars, quartz, any kind of loose grain that's sort of sitting around on the Earth's surface. Not quite as soil. Soil is different, but the soil does contain sediments. And then sedimentary rocks are those sediments that have been lithified. So in this picture, you kind of see both the rocks at the top and some interesting layers in there that are beds, which we call sometimes called cross beds. Okay? And then the sediments are down here at the bottom. How do we get the sediments, right? Because it's the sediments that produce, or the ions, the chemical ions in water that produce sedimentary rocks. Okay? Where does this stuff come from? It comes from the weathering process. So we could dissolve rocks at the Earth's surface. This is fairly common. Other types of processes like oxidation are common, as well as a process called hydrolysis. That's chemical weathering. Acids, typically like carbonic acid, interacting with the rock to break it down into minerals and ions. And those ions and minerals either get left at the surface, or in the case of ions, they get dissolved in water and carried down to an ocean. Okay? The other type of weathering that kind of helps out is mechanical weathering. This involves the physical breaking of rocks down into smaller pieces. Typically, if you break a material down into smaller pieces, it aids in the chemical reaction process. So it speeds up the reaction rates. So mechanical weathering aids or helps chemical weathering in breaking down rocks to make sediments. And here you go. Here are some sediments. Okay? The minerals that we see here, I'm going to highlight. That's quartz. That's quartz. Okay. We've got probably some hematite in here. Some other oxide minerals we cannot see here and here. Okay, maybe a feldspar right there, feldspar right there. So different minerals, but none of them are stuck together, right? If we want to stick the minerals together, we need to take them through the lithification process. Lithification holds the rock together and it involves a number of steps. The first step is deposition. Right? Deposition basically means you have a low basin, low topographic region, and we're going to pile up the sediments into the system. Okay, now, as you pile up sediments, the sediments at the top start pushing down at the sediments on the bottom, and so we get compaction. Okay, so deposition, compaction. A lot of times the sediments here at the bottom have water in them. They get squirted out, so you get dewatering. Okay. And then what happens is that things heat up a little bit down here at the bottom, and we get a change in the chemistry that allows for cement to be deposited and to hold the minerals together. So that's what all the yellow stuff is here. It's either going to be CaCO3, that's a mineral calcite, or SiO2, which is the mineral quartz. And that ends the process of lithification. It doesn't end the story for the rocks, but it's what takes us from loose, unconsolidated materials to something that is hard, okay, or indurated. There are three main types of sedimentary rocks: detrital rocks, chemical rocks, and organic rocks. And within the chemical classification, inorganic and biochemical are sort of two subcategories. And I thought we'd just look at what these look like in a few slides and think about how and where they form. Okay, So here are sedimentary rocks that are detrital, and you might ask yourself, well, how do we classify them? Just like we classify igneous rocks, we classify them with texture and with chemical composition. And so for detrital rocks, we're interested in grain size. You take a look at these three rocks. Just take a look at them for a second. Which one has the biggest grain size? Yeah, it's the one on the bottom left here, conglomerate. Okay? We classify it based on its size, and then the next most important thing is the chemical makeup. What are the minerals that are in the rock? How do we classify the other two? Well, which one is at the smallest grain size? Just give me a second to look. Yeah, shale is the finest grain size. Shale, conglomerate, and sandstone are all rock names for detrital rocks. Any rock that looks like it's fragments like this that have been glued together, fragments of minerals, that is, not fragments of shells, we'll call it detrital. Okay. Now, these are biochemical. Notice the difference. They've been lithified, they're fragments of shells, not minerals that have been loosely collected loosely and then compacted. This rock here is almost all shells. It's called coquina. Okay? And then if you look to the right, on the bottom right, we have something called fossiliferous limestone. The shells can get quite small. Here on the far right, you cannot see them. Right? They're microscopic. The skeletal remains of algae, bacteria, those kinds of things. Right? This is a bioclastic sedimentary rock. Okay? Where do these shells come from? They are made in water, so they're precipitated in water naturally by organisms, biologic organisms, which basically construct their own shell. And where does that material come from? Well, this particular rock, coquina, has the mineral CaCO3, and all of these ions that build out this particular mineral, which is calcite. Sorry about that. Let me erase that little bit there. Okay. Which is calcite. Okay. Come from the ocean water in which the organisms live. All right. Other examples of sedimentary rocks which are bioclastic, in particular, I'll just note chert. Okay, this one here is not made of CaCO3; it's made of SiO2 or quartz. So it's a different type of skeleton that's made by microscopic organisms in the ocean. Okay? Now we also have chemical rocks or inorganic chemical rocks. Where do these come from? Well, unlike igneous rocks where the mineral crystallizes from silicate liquid, now we're crystallizing these rocks from water. Okay, so the minerals are coming from, let's say, around the Great Salt Lake in a place that's dry, okay, collects water, has a high evaporation rate, and what results as the Playa Lake dries out is a crust of salts. These salts get buried in different layers, and this happens both in oceans and in these desert western desert environments in the western U.S. Okay, so these are inorganic chemical rocks. And then the last one is a no-brainer. Okay, it's coal. Okay? Coal is our only organic rock by definition. It doesn't even stand up to my definition of a rock, which is an aggregate of minerals and or glass. Coal contains some minerals, but primarily it is woody plant material. It's undergone a kind of chemical reaction through the process of lithification. So coal, okay, starts out in a swamp and gets buried, cooked up to a couple hundred degrees Celsius, and that organic material, which is partially broken down by bacteria and other processes early on, gets turned into coal. Okay? what do we care about sedimentary rocks? From an environmental standpoint, we might mine materials from sedimentary rocks. We might use them for building materials, and they may contain water. So they're important and connected to our interaction with the Earth and or near its surface. I should also point out that we like to investigate ancient rocks in a way, in an attempt to kind of understand the processes of the Earth. And so we simplify this a little bit. There's three parts to this diagram. There's the continental part. Okay. So some of those sedimentary rocks form on the continent in lake or glacial environments. And there's the marine environment. It's out here on the far sort of right. And these are rocks that form in the ocean, like decidedly in the ocean. Okay? Coral reefs, shallow marine, or even the deep ocean. And then there's the transitional zone, where you're looking at things like tidal flats, lagoons, and beaches, sometimes wet, sometimes dry, depending on tide, storm conditions, and so on. Okay, usually storms aren't that big, but certainly eustatic changes in sea level or global changes in sea level would affect these rocks quite a bit. Okay, so ultimately we're kind of interested in the depth from a historical standpoint and going back in Earth's history in the depositional environment of these rocks. And there are ways to look at rock type, for instance, and know that they're going to be marine, or another kind of rock might be continental, and yet a third might be transitional. All right, so that kind of sums up the variety of sedimentary rocks and the process of lithification. We don't have time to go through the details of how they all form, but you get the sense that they form in different ways, and that they can wind up in different depositional environments, which is both interesting from the perspective of tectonics and understanding the way the Earth works. From an environmental standpoint, one of the things we do is mine sedimentary rocks. And in fact, here in Illinois, we have very young glacial deposits that have been extensively mined for sand and gravel, which isn't very exciting, but it is used to make cement and to make road beds and other kinds of building materials, essentially. All right, so that does it for sedimentary rocks.